Hello, this is chapter 20 of Top Hat second edition. So for this one we're going to be talking about reactions involving aldehydes and ketones. This is the start of the series where we can talk about the carbonyl functional group. And so the generic one would be just a C double bond O, and it depends on what's on either side. So aldehydes have carbon on one side, hydrogen on the other. Ketones have carbons on both sides. Carboxylic acid has carbon on one side, OH on the other. An ester, carbon on one side, O carbon on the other. And amides have carbon on one side, nitrogen on the other. It doesn't necessarily matter what's hanging off of the nitrogen, but the important thing is that the nitrogen is directly hanging off of the C double bond O. This chapter we're going to be dealing with the aldehydes and ketones. Now, one of the things to remember about carbonyl chemistry is that the carbonyl group is going to be flat, because remember this carbon is sp2 hybrid. Okay, so because there's three groups hanging off of it, so it's spp, and that base structure is going to be trigonal planar, and so we're going to be having for a lot of these, right, we're going to be reacting at this, taking advantage of that polar covalent bond to be able to react at that at the partial positive here. Okay. So you've actually encountered quite a bit of aldehydes and ketones, because they usually have a scent to them. So one of the so butyraldehyde, it's has a buttery taste. If you oxidize this up to the carboxylic acid, to butyric acid, that actually is what happens when butter gets rancid. But vanilla, cinnamon, camphor, and the carbones, they've got the nice ketone group here. And depending on which enantiomer you're dealing with, you're either going to have spearmint or you're going to have sort of the savory caraway. And again, all of these, or I should say most of the chemistry involved in carbonyl reactions takes advantage of the partial positive and partial negative of the polar covalent C double bond O. Okay, and so this is going to be incredibly important from here on out. So if we want to make an aldehyde, right, so one of the things we can do is we can actually come in here and make them from primary alcohols. Okay, and in doing so, what we're going to be doing is converting CH bonds into CO bonds. Okay, so if we look at this carbon here, right, we're going to have we're going to have one carbon-carbon, one CO, and two CH. Now you're going to say, well, isn't there an OH bond? Yeah, well, there is, but we're only dealing with the carbon that that bond's directly attached to that carbon there. Okay, that hydrogen is directly attached here, and the oxidation is going to happen on the carbon that's holding the hydrogen. Okay? When we do one of these reactions, okay, whether we do Des-Martin or this pyridinium chlorochromate or the Swern oxidation, what we're going to be doing is we're going to be converting one of these, just one of these CH bonds into a new CO bond. Okay, so if you look at it here, right, what we've done is, we haven't done anything to that carbon-carbon bond here, but now we've got two CO bonds, right, and one CH. Okay, so how do you get two CO bonds on a carbon? The easiest way to do that is with a carbonyl group. Okay, so with a primary alcohol, when you do a one-step oxidation, so with that you're going to make the aldehyde. Okay, I should mention that all of these are do the exact same thing as far as reactions go. It's just giving you some options when you're trying to design a synthesis, but functionally they all do the same reaction. If you try to do this on a secondary alcohol, right? So you still have, right, if you're looking at this carbon here, because that's the one that has the oxygen, right? Now you've got one hydrogen on there. So if if you count for these, right, so you got 2 carbon-carbon bonds, right, going to each one of these R groups. 1 CO and then 1 CH, that bond. So we only have 1 bond that we can move. And so the new bond here, right, I'm not going to do any of those carbon-carbon bonds, but now you've got 2 CO and no CH. Okay, so that's all the farther we can go, even if we wanted to, okay, because we have no more CH bonds to be able to react. So with tertiary, and that's why with tertiary alcohols, okay, we can't oxidize them up to a CO bond easily because to the carbonyl, right? Because we don't have any, right? If you look here, there's 3 carbon-carbon bonds, right here, here, and here. There's 1 CO bond, but there's no CH bonds that we can use as currency or as fuel to be able to do the oxidation. Okay, so for tertiary alcohols, you can't simply oxidize that away. And so this is going to be important down the road when you're learning about things like the citric acid cycle. One of the steps is actually to move an oxygen over 1 CO in order to be able to continue to oxidize it, because you have to move it from a tertiary alcohol to a secondary. Okay, it's a pretty trivial step in that process, but in doing so, what you're doing is you're allowing the that alcohol to move from a tertiary, which can't get oxidized, to a secondary, which can. And so it's a small step in the citric acid cycle, but it's important, and it has to take advantage of the fact, and it has to overcome, I should say, the fact that the OH, which we want to oxidize, is sitting on tertiary, so we got to get it out of there. Okay. So if you're looking at this, right? So Swern, right? We're gonna convert 1 CH bond into a CO bond. Okay. So here is where the CO bond is. Okay. So right now, right, we've got 1 CH bond or CC bond right there, 2 CH. Because we've got only 2 bonds are shown, so there's there must be 2 CH bonds there, and then 1 CO bond. Okay, so what we're going to be doing is we're going to be converting one of these to a new CO. Okay? And so the way we do that, right, is to make the aldehyde. So if we're looking at this carbon again, right, we have 1 carbon-carbon. Right? Now we've converted, right, 1 CH right here. It's a bad H, sorry about that. The 2 CO bonds. With this one here, right, we're going to look at this carbon right here. Right? We have 3 carbon-carbon, 1 CO, right? But we don't have any CH bonds. Okay? There's no CH bonds on this carbon here. So that means that we don't have it, there's nothing that we can use to make an additional CO bond, so that means this is no reaction. Now for addition reactions, okay, the general mechanism is going to look like this. We're going to have some sort of nucleophile. It's going to have a set of lone pairs. So it has negative character. It's going to be attracted to the partial positive on this carbon here of the C double bond O. We're going to make a new bond here. That's going to push these electrons up onto this oxygen, right? So this carbon doesn't have 5 bonds. Okay, for that, and so you're going to end up with this intermediate here. The the O minus, during the workup of the reaction, you usually throw in some water, and that's going to get converted into an alcohol. So you're going to dump in some water at the end of the reaction, and that's going to grab that, and so you're going to end up with the OH. Like that. Now, you could think of it this way. So for this one, if we want to go backwards in the reaction, okay, if we want to do a reduction, okay, we can, if we have an aldehyde, right, we're going to be, we can convert an aldehyde into a primary alcohol, or we can do a ketone into a secondary alcohol, okay? And it's just the opposite for what we were doing before, right? This is, right, this was one carbon-carbon, right, 2 CO bonds, and one CH. Now when we do the reduction, okay, we're going to be converting one of these into a new CH bond. So if we look here, what we're going to be doing is we're going to be one CC, right? One CO bond, and then now we've got 2 CH. Same thing here. We're going from 2 CO bonds to 1. Okay, we're doing the rate. Now the way this has to work, okay, the reason why I brought up that mechanism, okay, is the fact that we're going to be using hydrogen as a nucleophile. Okay, and the way you have to do this is, one of the ways is lithium aluminum hydride, or LAH. Okay, this is a source of H minus. Okay. And so what we're going to get is we're going to get these lone pairs are going to react here, right? Because remember, that's a partial positive, partial negative. And then, so, right, and then these electrons are going to go up there because we don't want that carbon to have 5 bonds. And so this hydride here is this one right here. And it doesn't matter if you're an aldehyde or a ketone, it's going to work the exact same way. Now for this one we added some H plus, right? And to protonate this as the alcohol. Now you can't use NaH. Okay, so it oh, I should say there's also sodium borohydride. Okay, but it works pretty fairly similar. It's not as nucleophilic as lithium aluminum hydride. It's also not quite as reactive, stuff like that. So it's a little bit easier to handle, stuff like that. But it works it works very similarly between the two. Now, to say again, you can kind of think of these as you could think about as basically being this, and then so each one of these BH3s essentially has four hydrides that it can use to do a reduction. So if you do it if you put one molecule of this and one molecule of this, you will still have 3 hydrides left after this reaction to be able to react. So this can react actually 4 of these in theory. So if you're looking at this, right, LAH, right, this is a source of nucleophilic hydride, right, so that's going to react there, push that up. So you're going to end up with this. Right. And then during the workup, you're going to dump in a little bit of water, and that's going to grab that. And so you're going to end up with this. So this H here ended up right there. Now, one of the things we didn't talk about earlier are these organometallic compounds. Okay? And this is another way that you can get a carbanion, okay? A stabilized carbon nucleophile. Okay? Because the way you make these, okay, is that you have sort of an alkyl bromide, and you literally just mix in a little bit of lithium. And what happens is this gets displaced. This lithium displaces the bromine. And if you look at the what's going on with the this polar covalent bond here, right now it's partial positive, partial negative here. But when you make the, say, something like butyl lithium, okay, this switches. So now carbon is the more electronegative side. So it is partial negative, partial positive. And so you can think of this essentially as this carbon having a set of lone pairs with a lithium next to it. Okay. Well, this would be a CH2. Okay, so you can think about this as a carbon, a nucleophilic carbon, okay, with a lone pair. So you can have this. You can also have a Grignard what's called a Grignard reagent, where instead of lithium you put in magnesium. Now for these you actually have to keep around a one of the halides, right? So because remember, lithium is a +1, the carbon would be a -1. So if you look at the charges on here, let's say you did that exact same, right? So you have a CH2 negative. Remember, magnesium wants to be at a +2 charge, right? So you got a -1 and a +2. That means you need a bromine still around to balance out the charges. But they work essentially the same way. Okay, these are a little bit easier to make, and they're a little bit. They're a little bit easier to make, and they're not quite as sort of vigorous and reactive. So they're a little bit easier to handle. So. Now, one of the things to remember about these things is, remember, if you have a good nucleophile, it's also going to be a good base, something like that. And so for a lot of these things, so particularly for things like butyl lithium, they aren't always used as a nucleophile. Lots of times they're going to be used as an incredibly strong base. Okay? And so if you've got something like methyl Grignard or lithium aluminum hydride, or not lithium, butyl lithium, you're going to have you're going to be able to take off some fairly some pretty good CH bonds. So the terminal alkyne, usually you can use butyl lithium to get that away. Now you do have to be careful, right? Because if you get water or an alcohol in, mix that in with your organolithium or Grignard reagent, that carbon is going to grab this acidic hydrogen, and you're going to end up just with the with the alkane and a really expensive OH molecule or something like that. So you do have to be really careful to keep these reactions dry. But they can work as carbon nucleophiles. Okay, and they work like any other carbon nucleophile, right? So just like with the hydride, where this carbon group is going to attack here, it's going to push this up, and then in the workup, you're going to take this into an OH. Okay, works no differently than what we were doing with the hydride. It's just, in this case, instead of an H minus, it's a nucleophilic C minus. Okay. And so they can also do reactions where you would have, say, an SN2 reaction, right? So this CH2 here, right, it's going to act like it has a set of lone pairs. It's going to displace that bromine, right? Because this is where that polar covalent bond is. And so you can make. Actually, I think there's one too many carbons here. So you're gonna make this new bond here. Okay, so if you're looking at this, okay, so this carbon here, right, this is acting like it has a set of lone pairs. So there are two polar covalent bonds on this molecule. Okay. However, you can't really do a nucleophilic attack on a leaving group that's on a double bond. There's other things you have to do. So remember, you can't do that polar an SN2 reaction like that. So that means this this group is going to attack here, attack there, push that up, and then this is going to become the O-, which then becomes during the workup. Right? So we're going to get, I should say, let's go ahead and put this intermediate in here. And then during the workup, we're going to dump in some water, right, and that's going to grab this, keep that away. And so what you're going to end up with is this. And then the H from that water. Now for here, right? So you can make a Grignard or an organolithium off of a benzene, okay? But it's going to work exactly the same way. This carbon here is going to act like it has a set of lone pairs, and so lone pair electrons, and so it's going to be attracted to this partial positive, partial negative, and so it's going to attack here. That away, and so what you're going to end up with is this. So for it's just a very simple SN2 reaction. Right, it's just SN2. And then you've got this propyl group. That. You can see plus lithium chloride. Not too bad, right? Now, one of the things is with amines, okay, is they're going to react a little differently. Although it ends up working out, the reaction still occurs where you come in here and you have an amine, right? Here's a set of lone pairs. It's still going to attack here, okay? But what's going to happen is you're going to end up removing a water molecule, okay? And so what ends up happening is these two, this nitrogen is going to come in and replace this oxygen here, okay? And this oxygen and these two hydrogens are going to come together to make this water molecule, okay? Because remember, it's HOH there, okay? And so you're still going to get a reaction here, but after it rearranges, you're going to get this imine, or sometimes in biology it's called a Schiff base. And so when you look at something like this, right, we have a primary amine. That's going to replace this oxygen here, and so we're going to get this. Plus there you go. Now you can see this, so this is a very, very, very common reaction in biology, okay? Where you've got, say, you've got a protein, you've got an amine, a primary amine on a lysine amino acid. If you react this with an aldehyde, okay, you're going to get that displacement, right? OH. This OH is going to grab, right? This OH is going to grab that hydrogen, and that's going to collapse that down. So that, and you're going to get the loss of water to go here. Now this C double bond N is going to react very similarly. The Schiff base is going to react very similar to a C double bond O. So you can have another nitrogen, and this should actually be here. And actually, this arrow is supposed to go that way. Okay. That's going to react there. Push this up, and then you're going to end up with a hydrogen here. So this is a way you can cross-link two different proteins to stick them together. Okay. Now with secondary amines, this is one where we only have one hydrogen on there. One hydrogen on the nitrogen. Okay, we don't have enough hydrogens to remove that water. Okay, and so we're still going to get that same reaction, but instead of having both hydrogens come off the nitrogen, we're going to have to take off a hydrogen that's on an adjacent carbon, and what that's going to end up doing is leaving a double bond here. So that wherever that you're ripping off that hydrogen, that's where the carbon is, or that's where the double bond is going to end up. And so this is what's called an enamine, right? So it's an ene for alkene, right? And then amine for the fact that you're making a new amine. Okay. And so if you've got this, right? So this nitrogen is here, right? So look at it that way. So we're still going to replace that hydrogen, okay? But what's going to happen is the second hydrogen needs to come from over here, so that means that the new double bond is going to be there. Right? And so in this case, one of those hydrogens is coming from here, and the other two are coming from here and there. So that's where the water is coming in. Okay, so the last one is reduction of an aldehyde or ketone to an alkane. Okay, there's two different ways that you can do this, or there's a couple of different ways you can do this. The first one is called Wolff-Kishner, and it uses hydrazine, which is just essentially two ammonia molecules stitched together. Okay, and this is done under basic conditions. And essentially, all you do is you come in here and you just erase that. That's it. For here, all I'm doing, right? So is again, you're doing is just erasing that, and so here are our 5 carbons there. That's it. It's not too bad. You can also do it under acidic conditions, and this is what's called a Clemmenson reaction, and uses a zinc-mercury amalgam under acidic conditions. But essentially you do the same thing. You remove the C double bond O and replace it with a CH2. Okay. That's it. That's all it is. And so if you're going here, right? Aha! We have hydrazine, which is one of the few times you see this. Okay. Aha! We're going to be doing this, right? We know that we're going to take out that C double bond O, and so our new product is going to be right. It's just simply going to be that, right? Cyclohexane. For here. Right? Again, we're going to be just taking out that C double bond O. And so that's it. That's all it is. Now, why would you want to have two different two reactions to do the exact same thing? Well, it actually it provides some flexibility when the molecule gets more complex, because some groups are sensitive to acids, some groups are sensitive to base, and so if you want to react at this end of the molecule, okay, with your to do this type of reaction, But a functional group over here, it's sensitive to acid, right? It'll decompose an acid or react under acidic conditions. Well, then what you need to do is you need to use the Wolff-Kishner. If instead you want to react over here, but the groups over here are sensitive to base, well, then you should probably use the Clemmenson reduction for that. And so it helps you to, it gives you some flexibility when when the molecules get a little bit bigger. So that's it. Good luck.